Section 4 is all about the next rule that you guys need to know. It's called the chain rule. So we have the product rule, we have the quotient rule, we have our general basic rules for differentiation. We called it the power rule and some of those other ones, the constant rule and things like that. So now we have the chain rule. And this one is incredibly powerful. It's way better than anything you've done so far. The chain rule is used when we're dealing with composite functions. Composite functions are functions that are composed of other functions. We called those Fogg and Goff in algebra. You guys remember those? You had the notation f composed of g of x, or g composed of f of x. Anytime you have a function composed of another function and you're trying to take the derivative, you're going to need the chain rule. Derivatives that we can take, these guys here, we can take all those. The derivative of the first would be 2x, the second would be cosine x, the third would be 3, the fourth would be 1 plus secant squared x, right? We can do those in our heads at this point, hopefully. At least I can, so I'm thinking you can too. General rule in calculus, if I can do it in my head, so can you. Derivatives you can't take yet, and the reason you can't take them is because they are functions that are composed of other functions. So notice the similarity between the two columns. We have over here y equals x squared plus 1. Over here we have y equals, again, the x squared plus 1, but now we're taking the square root of it. We have y equals sine x over there, but now we have y equals sine of 6x here. Y equals 3x plus 2, but now we have y equals 3x plus 2 raised to the 5th power. I suppose you could FOIL that out and then multiply in another 3x plus 2, and then do that 2 more times after that. Or you could use the binomial theorem in Pascal's triangle to expand it, and then take the derivative that way. But really, you can do this in your head. You'll be able to do that pretty soon. You'll be able to do this one in your head. Y equals x plus tangent x, but now we have y equals x plus tangent x squared. And this brings up a really good point. Does this mean that the tangent of x is being squared? Does it mean that the tangent, this is the tangent of x squared? What does this mean? Take the tangent of x squared. Yes, that's what's going on there. So you need to recognize notation too. Tangent squared x would be there. That would mean tangent squared like that. Tangent x, the quantity squared. But with this squared just sitting here, that's on the x. Okay? So similarities and differences. We have the original function sitting over here. Again, back over here. But now each one of these is composed of a new function. So that new function has that original function placed inside of it. These all require the chain rule. Okay? All right. All right, the setup for the chain rule. If you picture a chain, like a link chain, it has links on it. That's why it's called the chain rule. This is kind of the same idea. You are basically linking together what you started with to get to what you finish with. And let me set this up before we talk about the notation that's going on here. If I have, let me think, like 3/4 maybe. I can split 3/4 up. So if I have 3/4, I can split that up into 3 over 1 times 1 over 4. You guys agree with that? Okay. So now right here, that's kind of like 1 times 1, or 1 divided by 1 right there. That's like a fancy one of 1 over 1. So it's pretty mundane right now. But I could put something interesting in here. Like I could put a sunshine and a sunshine right here. And now I have 3 divided by sunshine times sunshine divided by 4. What does it reduce to? 3/4. Okay? So that's the idea of the chain rule. Now notice that I started with this, and then I have that, and now I have this. So it's like 3 links of a chain, kind of. This reduces down to the 3/4 that I started off with. The same idea can be applied to this. It's not actually what's going on here, but you can think of it that way. If I start with dy over dx, which is my notation for what? Taking the derivative. Okay? if I have dy over dx, I can split that into dy over 1 times 1 over dx. And now I have that fancy 1 situation happening right there. So I can put whatever I want in there. What I'm going to do is I'm going to put what we're going to refer to as a du. So instead of dy over dx, we'll have dy over du, right there, times du over dx. The du is going to represent a new function that we are going to create in terms of u. We're going to take the derivative with respect to u and multiply it times the derivative of the u function with respect to x. That's what that means right there. Now, as you curl up into the fetal position and start to weep softly, it's not that big a deal, okay? Look at this. We have du over du. What is that? It's 1. Times dy over 1 times 1 over dx. That's exactly what I have sitting right here. That's just a fancy 1 sitting there. Now, instead of that fancy 1 sitting there, I'm taking this guy and I'm putting it there, and I'm taking that guy and putting it there, and that gives me the chain rule. Okay? This right here, dy over du times du over dx, is the chain rule. It allows you to take derivatives of compositions of functions. So the better way to look at the chain rule is like this. This is like the highly formal, non-formal, partially incorrect way to show you the chain rule. Better way to look at the chain rule is like this. If you have a function that's composed of another, so f of x that is composed of g of x, it would look like this. I'm taking the derivative with respect to x of f composed of g of x. That's what that says. The derivative would be f prime composed of g of x times g prime of x. Now, isn't that clearer than the other? Can you sense I shouldn't be using sarcasm? Maybe? No, I don't think this is very clear at all. So what I'm going to show you is the more clear way to put this, okay? But what you have is a function composed of another function. What this is saying is I can take the derivative of the outer function and multiply it times the derivative of the inner function. That's really what's going on. Okay? All right. When I take the derivative of the outer function, the inner function will not change. But then I have to multiply on the derivative of the inner function. I think that probably explains it a little bit better. Okay. The third way to remember the chain rule is, I think, the best. It's the derivative of the outer function, keep the inner function the same, times the derivative of the inner function. In other words, y prime equals f prime u times u prime. F prime u times u prime, that's the chain rule. That's what you need to know. So first we need to practice recognizing the inner function. So we need to know which function is the inner function, which function is the outer function, okay? We're going to let u equal the inner function. And we're going to write let u equal whatever that inner function is when we start doing practice problems. Then the outer function will be the thing that we compose with the inner function. So here we go. What is the inner function here? What is g of x? Good. U equals 2x cubed plus 1. That is something we can take the derivative of. So what would y be then as a function of u? If u equals 2x to the third plus 1, I can take u and substitute it in here. What am I left with? Y equals u squared. So now, just as a little tease of what's to come, I can take the derivative of this function. I'd be taking the derivative of u with respect to x, du over dx. I can take the derivative of this function. That would be taking the derivative of y with respect to u, dy over du. Okay? So that's where that notation came from. But if we remember y prime equals f prime u times u prime, then we can avoid having to deal with that notation. So what is the inner function here? So I'll write let u equal 4 minus x squared, the inner function, which makes y equal 3 u to the 5th. Okay? Recognize the inner function. Let u be that inner function. Then substitute it in and write the outer function. So what is the inner function with y equals sine 2x? It is 2x, yeah. So u equals 2x. And once I have that, then I have y equals sine u. Notice that we can take the derivative of sine u. If you look at the inside cover of your book, the derivative is written sine u. Take the derivative of sine u and you get whatever it says, okay? So they're actually showing the chain rule for everything. G of x is the inner function. We're going to let u equal the inner function. And then f of x will become, or sorry, f of u will become the outer function. Finally, the last one, y equals cosine squared x. What is the inner function? No. U will never be x. That doesn't do you any good. You're just changing variables. Cosine squared is the function you're looking at. Why? Yes. If you rewrite this as cosine x squared, now you can easily see that the inner function here is cosine. So u equals cosine x, which makes y equal u squared. These problems become very easy. Once you get fluent with the chain rule, taking the derivative of problems like this is actually fairly straightforward. You can do it in your head most of the time, especially involving trig functions. If it's a polynomial or some crazy rational function thing, you're probably not going to be able to do it in your head, and you will want to write stuff down, as we're about to do with practice problems. All right, find the derivative of y equals the quantity x squared plus 1 to the 3rd power. So the first thing we want to do is recognize that we're not going to use the product rule here. We're not going to use the chain rule here. We have a function composed of another function. We're not going to use the quotient rule here. We are going to use the chain rule here because we have a function composed of another function. So we need to define u. We're going to write let u equal whatever that inner function is. What is it? X squared plus 1. Now the chain rule, I'm going to rewrite over here. Y prime equals f prime of u times u prime. So this is the derivative of our function expressed in terms of u. This is the derivative of u right here, okay? So we have u sitting here. We're going to have to take the derivative of u. So u prime equals 2x. Now we have this piece right here. We need to rewrite our function y in terms of u. So y equals what? U to the 3rd, that's right. This says we need to take the derivative of our function in terms of u. So let's do that. Y prime equals 3u squared. But y prime also has to have u prime tacked onto the end of it. So times that 2x. Now we back substitute and rewrite our equation. Y prime equals, the 3 is out front, times that 2x, which becomes 6x. And then in parentheses, I back substitute what u was in the first place, x squared plus 1. But it's squared. So that's my answer. So let's take a look back at the chain rule, not the notation for finding the derivative using the chain rule. The chain rule said dy over du times du over dx, right? Okay. Where is du over dx? The derivative of u with respect to x. Where is that at? U prime equals 2x. This was found right there. Where is this? dy over du. The derivative of y with respect to u. Where did we do that? That is the original with respect to u. So yeah, this is here. Okay? So we actually did the chain rule here using this notation. All right, so that's out of the way. Based on what you see above, is there a shortcut that might work here? What? No. You started off good. What happened? It decreased by 1, right? We had x squared plus 1 to the third. It became x squared plus 1 squared. Where did the 3 go? Out front. God! We still had to multiply times u prime. Okay? So really, I could have written y prime equals, the 3 goes out front, times what's inside, decay the exponent by 1, times u prime. Then simplify. We did. We do. We need to. Need to do that, okay? Get in the habit of doing this still, because we are going to do that all year long, and there is a very specific reason why. This right here, if you can do this step on your own without writing it down, then fine. But this is a very basic problem. There are going to be problems that are way more challenging than this where you will want to write things down as you go. Okay? But yeah, if you can do things in your head, then do things in your head, absolutely. This is a special rule of the chain rule. It's like a corollary to the chain rule almost. It's called the general power rule. It's just a special case of the chain rule. It only works when you have stuff raised to a power. This is the formal notation for it right here. If y equals some function in terms of u to the n, so some stuff to a power, then y prime equals, you can take the n and write it out front, times the original function inside, decay the exponent by 1, and then multiply on du over dx, meaning take the derivative of what's inside and tack it onto the end. That is the general power rule. You want to see that and recognize it and use it as often as you can. And it's usually going to happen when you have some stuff to a power. Could be a rational function, could be just a polynomial, could be trig functions inside there. As long as it's stuff to a power, you can use the general power rule. So in other words, the simplified version of that is y prime equals n u to the n minus 1 u prime. Just get used to how to work with the general power rule, and you won't have to remember either of those. So find the derivative of f of x equals the quantity 3x minus 2x squared to the third power. Is that a general power rule situation? It's definitely a chain rule situation. We have an inner function here. Okay? So let's use the general power rule. F prime of x equals 3. So the 3 came from the exponent coming down. The stuff inside stays the same. Decay the exponent by 1. Then times u prime, and u here is the inner function, so take the derivative. 3 minus 4x. I call that done. You might simplify and distribute the 3 in. If the back of the book did that, then you would want to do that too, but this is good enough, I think, right here. The calculus is over, the algebra is completely eradicated. For now.